Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello and welcome everybody.
Yeah, don't block the clown face.
That's right.
You're blocking the clown face. I had to move. I moved the camera so I wouldn't block the clown face, but
Yes.
or the words. But it's very important, you know.
Yes. That
So-
we have our
meme.
our weekly meme or message for the people who join our live stream.
Exactly. I like when we get questions about it because I don't usually make reference to it. Although we're doing that very first thing now because that's apparently what you do is you make. That's the coolest thing to do with a joke. Is to explain and reference the joke explicitly. That's the key to comedy.
Yes. Yeah.
The funny thing is I made a bunch of these as my recent foray into, memes or whatever.
Mhm.
And some of them are I actually think they're pretty funny.
Yes.
But the text was too small. It's hard to read.
Oh yeah.
Just you can go to these meme making websites like you can find it, it's easy. And it's like for right here, like behind us, you know what I mean? Like there's only so much real estate, so it's a little small. It's hard to read. So that's on me.
That's
so I won't use the ones that you can't read because it's not funny unless someone can read it and then get mildly upset or say, "What's that about?" Like the one with the impedance baseline.
Oh yeah.
and then I kind of went on a rant about it, which I tend to do. It's kind of my calling card.
It's good. It's good. No, I think it's good. It creates engagement. You guys are asking questions about it. It may even be about stuff you've never heard about, although probably someone will ask you about this.
I hope so.
That's my guess. And
I hope so because it's fun to get angry every single week at 1 p.m. on Fridays. It's my thing.
Yes.
Oh. I feel attacked.
Yeah,
welcome, Ferris. It's a truth. I hope it is a truth that you need to hear because if you feel attacked, just know I'm attacking you. So. And with that, let's attack this first question. See that segue?
Yeah, you did a good one there.
That's how professionals do it here.
Yes.
So,
I'm
trying to see if it's like Sinavasan. I was wondering if it was like, anyway, if it was like seen Ivan, like it was a couple of words or
a couple of words.
It's always tough with the user names and things like that.
Could be anything. Could be a Pokemon.
Could be a Pokemon. That's true. As we've found. Anyway, that being said, this person has said that a negatrode, which I'm not sure what that means. I suppose
we're just going to call it an electrode.
Yeah, it's a combination of negative and electrode. I'm guessing,
yes.
But I've never seen. It looks. You know what it looks like too. And I'm getting way distracted here and I can't help myself. It looks like a transformer. That's what, right, I've never seen any of those movies because they look really stupid. Yeah. But it's like Megatron is one of them.
Exactly. That's right. It's Megatron and this is
Negatrode. Is Megatron a good guy or a bad guy?
He's a bad guy.
Okay, so Negatrode will be a good guy and he can fight.
Although I guess it depends on your point of view, but yes, he's supposed to be a bad guy.
Okay, that's true. Yeah, he could be your good guy if you have a different viewpoint.
If you have a different point of view.
Okay, so a good guy from the Transformers movie is comprised of iron hydroxide and a supercapacitor, 2 molar KOH. Okay. So the question is, which redox reaction is the reason for charge storage? So literature strongly mentioned potassium intercalation, but I feel formation of oxyhydroxide basically. I'll be honest that I don't have direct knowledge or experience of potassium intercalation. I suppose I ought not to doubt outright this as a possibility if there's literature reports of it. Maybe there's good reason, and it's certainly possible. It's something that I don't. I don't understand this. It just seems kind of unusual to me for a couple of reasons. One of them is that potassium is an alkali metal. It's the row below lithium on the periodic table. Now I know an intercalation reaction is not the same as like a standard redox reaction, but like what, for example, on like lithium ion batteries, one of the reasons why it's so useful is that the lithium, like Li plus an electron to like solid lithium is like 3.05 volts. Like it has a very high E0. It's one of the reasons why it's such a great material. It's such a great ion for for batteries, because it has a high voltage, and so you can get a lot of power out of it and everything. Potassium is like 2.85, like it's minus 2.85, but it's like it's in the same boat. And what that means is that it's one of the reasons why something like KOH or KNO3 or KCl are all great electrolytes, because you're never going to oxidize or reduce potassium in an aqueous solution. Like you're just not. You will rip water apart before you get to a potential high or low enough to do anything to the potassium itself, for the most part. So I have some skepticism, let's just say, about the chances that potassium will do almost anything in like aqueous solution under normal conditions. Again, that isn't to say that this isn't happening, because it very well might be, and I'm just misunderstanding this intercalation reaction. But in an aqueous solution in an alkaline supercapacitor system, it seems a little strange to me. All I can sort of speak to is a couple of things. One is that on a supercapacitor, I may be misunderstanding perhaps, but like the phenomenon of the double layer capacitance and the inner Helmholtz plane. My understanding with a supercapacitor is it just has a tremendous surface area, and it's a material that forms a very, strong, high capacitance sort of naturally, so that it'll have a probably really thin and very robust capacitance on its surface. And I don't know that it almost seems contradictory to be looking for an auxiliary charge storage mechanism, because if it's a supercapacitor, capacitance would not capacitance be the charge storage mechanism? And again, I might be misunderstanding some of this, because like with a battery, for instance, the charge storage mechanism could be a number of things. It could be an intercalation reaction, it could be a conversion reaction, it could be an alloying reaction. There's options, but we classify those as batteries. It's like it's a classification of energy storage device where there could be a number of different electrochemical processes that contribute to the charge storage. My understanding, which again fully acknowledged could be flawed here, is that a supercapacitor's primary charge storage mechanism would be capacitance. So it seems strange. I'm just sort of fundamentally confused in the idea of trying to associate the reason for charge storage to anything other than the capacitance itself. It just seems bizarre to me. It could, like I said, it could be the case that there's maybe this like a secondary mechanism of charge storage. And what I'll say about the oxyhydroxide is I have some experience working in alkaline electrochemistry, for instance. And it seems unlikely to me that you would classify charge storage through the oxidation of, let's say, Fe2 to Fe plus 2 plus to Fe3 plus, which is what you get when you go from iron hydroxide to iron oxyhydroxide. That's an oxidation reaction from 2 plus to 3 plus oxidation state, and it's just a redox reaction. Like I wouldn't classify that as necessarily as charge storage per se. It's a pretty normal transition metal hydroxide reaction that will undergo at whatever positive potential is associated with that catalyst. It seems strange to me to even classify that as a charge storage mechanism, I guess. Like it's just like if you go to a high enough potential, this will oxidize to the +3 form. And I don't know that it's like relevant to call that a charge storage mechanism. I don't know. Give me some of your thoughts.
Yeah.
Maybe it can be, and I'm misinterpreting.
And another thing, just to, because you may not have seen it, Ferris Whitehouse was just saying you'll get charge storage through iron to iron oxide, the Edison battery anode, which I actually don't know enough about that. But this is a good question. I guess the thoughts that I have about this is, yeah, when you oxidize or reduce something, and almost like a redox flow battery, like that's a way you can like quote store charge, and then
Mhm.
you get the electrons out by oxidizing it, or you put the electrons in by reducing it, whatever the molecule is. And then I've also heard, actually from a lot of people who attend the live stream, about pseudo capacitance.
Yes.
So you're right. I think that when it comes to supercapacitors, electrical double layer is the primary mode of charge storage through the double layer, because you end up getting these really, really high capacitance values. But pseudo capacitors effectively store charge, or basically they have a surface bound Faradaic reaction, just
Mm.
like iron 2 plus iron 3 plus, um, that allows it to, like, okay, well, in addition to the double layer, it's also storing charge through a reaction as well.
Yeah. Maybe
And
that's
some people have some controversy about that. Not going to get into it. Some people don't think it's real, but um, okay, and see, the person who's asking the question is saying, uh, I could put like pseudocapacitance charges through surface redox reactions. Yeah,
yeah. So
yeah,
I
yeah,
think that's probably
yeah,
yeah.
yeah. Surface redox reactions basically is how
Yeah.
they're thinking
So
about it.
I think it's probably a bit of what I said. It isn't
Mhm.
likely, or that I'm, maybe misunderstanding perhaps a little, or just misrepresenting, let's say. Um, but yeah, to a certain extent, it's kind of like, I don't know what you call auxiliary charge storage mechanism in addition to the capacitance, the double layer, so to speak.
Mhm.
Maybe some of this redox reaction. I would have to look. I mean, the short answer for the potassium thing is I'd have to look at the literature and kind of read about that. I'm not familiar with a potassium intercalation
Yeah.
in aqueous, right? Like lithium
Mhm.
intercalates in a battery, sodium ion batteries, zinc ion,
Mhm.
like those are battery contexts with high voltages and non-aqueous electrolyte and things like that. You'll get, intercalation, deintercalation. That's the primary charge storage mechanism usually for a battery. I'm just not aware of that kind of thing not only happening with a supercapacitor, but being physically possible in an aqueous system where you're very limited on your voltage window. So
Mhm.
maybe it is a thing. I'm just not really aware of how that could happen.
Yeah.
So anyway, thank you for the question.
Yeah. Yeah.
Hope that kind of talks through a little bit of it. Follow through again. See, you're probably still watching. So if you
Mhm.
have a follow up question, please type it in. We'll, we're happy to talk
Yeah.
about it some more if you want to follow up. So.
Yeah. Absolutely. Let's see. I guess so. Lino Saako is next. Lino's asking, "Hi everyone. Why do screen printed carbon electrodes show a voltammetric peak even in inert electrolytes, potassium chloride, if carbon shouldn't produce a signal?" I think my initial thought is that there probably is something in the carbon. Like, yes, if you have a clean, polished, traditional glassy carbon electrode, and you put it in a potassium chloride solution, if you sweep within a reasonable voltage potential range, maybe you'll see like very small bumps, but you won't. It'll be more or less double layer charging. That should be the current that you get. So, why is it in a screen printed electrode you end up seeing some kind of signal or what looks like a voltammetric peak? We've seen stuff like this before. Ultimately, my initial thoughts are that these screen print electrodes, they're made and then they're allowed to just sit out, and they're not polished. So stuff gets on the surface. Some junk sometimes will get on the surface. Now, most of the time when you buy our electrodes, like our screen printed electrodes, they're packaged, they're sealed, they're in a nice container, um, and they're pretty stable. But oftentimes, uh, each batch is a little bit different because of the carbon ink formulation. And sometimes what's a good thing to do, Lino, is to actually take your carbon screen print electrode and then do some cyclic voltammetry, some CV sweeps. Say you do it in something like a dilute acid, and you can try to actually oxidize a potential contaminant off. That's what I think is probably happening. And only in some, dilute sulfuric acid solutions would you observe or be able to remove the potential contaminant. I think that what you have is most likely a contaminant. It could be some volatile organic that just has an affinity for carbon, right? Because the carbon surface just by itself isn't just pure carbon. It's got some water, it got some OH groups, it may have a carboxylic acid, who knows? But it has it may have some stuff on it, and you're literally just getting, removing it by cleaning it electrochemically. So, so when you see this voltammetric peak, you may need to do a little bit of electrochemical cleaning to remove it, and then you should, in principle, have a good looking voltammogram from your carbon screen printed electrode. So let me know if that makes sense. We do have quite a few questions that are coming in. So if you do have questions or further up follow-ups, please let us know. So thank you, Leno. I hope Leno Skako.
It's got 3 C's.
Three C's.
Skako.
Skako.
Lino Skako.
No, Skako.
Okay. Next, we have a question from Zara. It looks
Mhm.
like, how do I calculate peak height using square wave voltammetry when my peak is sloped? What baseline shift method is appropriate? I'm scanning cathodically. Let me share my screen here because I have our software. I kind of grabbed a CV. Note that I know it's not necessarily square wave, but the phenomenon is roughly the same.
Yeah.
So here's a CV. So just whether this is again, whether this is a square wave or not, and I got one. I tried to get it relatively sloped, actually. You can see that it's kind of sloped. I don't know if it's what you mean exactly by sloped, but what I'll do is I'll add a peak height tool here. I know you can't see like the right click menu here, but the peak height tool is here. So, I mean, the short answer of what's usually done is, if you're looking at, like, for example, this is forget about the tool for a second, right? One of the things that you can do for the peak height, you just take this value up here. So forget about this this window here, the value that's saying, look up at the top here. This is where my mouse is. You might look at this and say, like, okay, well, this is at a whatever minus 130 millivolts, whatever this value is. I'm looking at the oxidation peak, but it's the same just for cathodic. It doesn't matter which direction you're going. You'd say, okay, this is 31 microamps. Okay, well, you're trying to get a baseline. You want to subtract a baseline. So, well, is the baseline 0? Well, in this case, like you're saying, is everything's kind of sloped. So really, the answer is that you're trying to get it's kind of the intersection of two lines. That's what this baseline tool does. So I'll draw the baseline out kind of far. So what you're seeing here is that I can kind of draw this baseline sort of wherever I want. I can actually kind of, so this is a regression. What I can do is, let's just do like free slope. So I'll just play with it and kind of show you. So I can move the baseline sort of wherever I want. Free slope. I picked the wrong one. Oh, that's where it is. Okay. I should have to move the points around. So if I'm trying to account for, let's say I wanted it to be perfectly 0, right? It's like I could move the baseline to be like perfectly 0, and that would be like, oh, that might be your assumption of like, this is why peak height should be. It should be based on 0, and I'll get 30 microamps. But you might also say to yourself, right, that I want to again take into account the slope that's of my graph, and so now my peak height's going to be different because it's the intersection of this not straight 0 flat line, or if my baseline was like up here for whatever reason, then my peak height's going to be smaller because it's a difference of different lines. So really the answer is either you have software like this that allows you to kind of manipulate a peak height based on whatever kind of baseline that you want. Maybe that's an analytical tool that you just need to get your hands on, basically. Or, perhaps the way your stuff is sloped or something is a little more severe, perhaps. I don't know. I'd have to probably maybe understand what your data look like,
Mhm.
perhaps a little more, but something like that is usually what's done, is that we're finding kind of the intersection between sloped lines when we account for a sloped baseline. It's the best
Mhm.
that we can do,
Yeah.
because the reality, of course, is that in electrochemistry, even when we're like doing rotating experiments when it's supposed to be perfectly flat and, you know, mass transport controlled and all that stuff, it just almost never is. It's never perfectly flat. So we sort of try to make these I don't know, assumptions, and we do these tricks with this sloped baselines to try to account for that. So that's kind of my advice, I guess.
Mhm. Yeah, no, I think that's good. I think using that tool, it doesn't matter if it's square wave or
Right.
CV or anything else. All right, moving on. Next question. Aminora Ovovac 5323.
You're doing great with these
Yeah,
names.
just going for the names. Uh, what's a good trick for better understanding electrochemistry? This is a
It's a trick.
it's a great question.
Watch every one of our YouTube videos.
That helps a lot.
That's a trick.
You know, you can read books, can attend classes, read papers, do experiments. It's always good. I would definitely watch our videos on our YouTube channel. And then if you're done watching, 15-minute long videos and you want something a little meatier, I would join to become maybe a tier 2 YouTube member where you can watch all of our webinars, which are longer, full length videos, almost like courses, really. On electrochemistry and different topics. So, cyclic voltammetry, impedance spectroscopy, rotating disc electrodes. Neil just did one on semiconductors, MoS₂. So these are ways of consuming electrochemistry content to help you understand things a little bit better. So you may spend a bunch of time reading textbooks, trying to get a better understanding for things. Some of it's maybe not sticking. You just need to hear about it a little bit differently. So that's one thing. Attending these live streams and then asking us questions that you run into is another very helpful thing to do, because a lot of stuff is coursework, and it's just like, oh, I have no, I don't get this point. I can't, I can't move past IR drop. I don't know what IR drop is. It's like, well, ask us about it, and then we can explain it, and then that will help you like move forward with your learning of electrochemistry. The last thing that I'll mention is, Pine Research not only has this YouTube channel and this live stream, as well as webinars, but we have articles on our website, but we also host workshops. So I'm hoping beginning of next year, 2026, we'll actually have a list of workshops that we collaborate with different universities to hold workshops on electrochemistry, specifically cyclic voltammetry, maybe a little bit of EIS, things of that nature. So uh, it's possible that if you're in the United States, you can attend one of these workshops and get real hands-on experience with learning electrochemistry. So that's it. Those are all the tricks. If you have more questions, please let us know. Thank you.
Those are the tricks.
Those are the tricks. All right. Moving on, because the questions today are coming in. I think everyone's getting ready for next week because it's the Thanksgiving holiday here, and we will unfortunately not be here next
Correct.
week. So, getting your questions in now rather than later is a fantastic
Yes.
idea. Or you're all scrambling for midterms right now.
I will all be. We will be in a. I will be in a food coma next week and unable to talk about electrochemistry.
Yes, I will be hopefully next week Friday working out intensely due to the food coma that I will have had the
I will
previous
be
day.
not working out, but still enjoying the food.
Still enjoying the food coma.
Very likely will be doing no physical activity whatsoever. So yes.
Okay. All right. Next one. All right. Let's go. Kalpanaselam 5392.
You got the last part.
I got the last part, the 5392.
That's right. You did a good job.
Thank you. Is asking, CV curve, the voltage at some. I'm sorry, that's very funny. I got the numbers right. in a CV curve, the voltage at some points suddenly dropping, and the next second, it continuous in the curve. Can you please tell the reason? And at what point the dropping instrument and at the point of dropping instrument showing overload blink. Okay, so my initial thoughts, I guess, are this. So let me just share my screen. I think what you're observing, and I think I should be sharing.
Yes, you are
No,
good.
no problems. It's like, all right, this is your voltage, this is your current, and you're doing your CV, everything's looking good, and then bam, you get this thing, and then it
Sound
just
like Emerald
yeah,
Lagasse.
yeah, it goes like this, and you have stuff like this, right? Everything
It looks like a shark.
looks kind of like a shark, right?
We
So
need a screenshot of this too.
so
This is better than my
this
smiley
is better than
faces.
your other smiley face. So you got these weird outliers here.
It looks like a narwhal.
A narwhal. You got these outliers here. This is normal. These are normal parts of your voltammogram. But you're trying to figure out what this is. And honestly, it depends a lot on the nature of what it looks like. So there are instances where you just get these, but there are instances where you get like these, and these things occur periodically. You know, I've seen I've seen stuff like
Now
this.
it looks like a dinosaur.
Now it looks like a dinosaur. Because if you have something like this, there may be a degree of constant, like bubbling, noise, even little like frequency bumps. You could be the sampling rate of your potentiostat may be so high that it's picking up these trace things. So potentiostats have filters that are used to kind of smooth the data out. Otherwise, your data may look very, very noisy, very choppy, but you have lots and lots of data points, right? But and I mean, sometimes the data points are really, really choppy, but you're collecting every single data point. You really know the value quite well, but it looks terrible. Oftentimes we just want a smooth line, so we'll use filters. The problem with using too many filters is that you could lose signal. It's possible that this is a real thing. This is a demonstration of contamination, and in your CV it just kind of looks like this, and it's there, but it's kind of filtered out. But it's important that you know that that's there. So when you see stuff like this, it's usually this you're looking at current, right? You're looking at this current spike. And sometimes this has to do with disruptions, like a real mass transport related issue in your system. Oftentimes, I've observed this is due to micro bubbles popping. So if you're doing some kind of catalysis experiment, and let's just make a new slide. So let's say you're doing some kind of catalysis experiment, and this is your electrode surface. Your redox reactions are occurring. With an electron goes to R, but basically you'll form these little tiny bubbles. Maybe it's hydrogen evolution, oxygen evolution. But when any one of these little bubbles pops, because it got big, and then it leaves the surface, it's leaving, you have a flood of new solution coming in. And that flood creates a current spike. So sometimes these problems are almost unavoidable. They can change based on the potential, how your electrode is polished. Sometimes they're very difficult to observe, but usually, if that's the case, and actually I should check, is there been confirmation? I don't think I've seen any confirmation.
I can't remember whose question this was.
This is. I got the last
which numbers?
Which numbers? It's
no, not 51.
5392.
There it
This
is.
one. Yeah.
Okay, I haven't seen a
I haven't
follow-up yet.
seen
I'll
any
check,
follow.
but keep going.
But yeah, this is basically this is basically this is what I think sometimes causes these kinds of issues. But when you observe them, when you generally observe these kinds of little spikes, that is what it's due to. And sometimes it can be corrected by changing the filter settings a little bit, maybe the current range. If the overload light blinks, the overload light might blink for a second because you may have a current range that you've exceeded. This may be 100 microamps, and you've exceeded that current in the instance where where the bubble popped or the current spike occurred. So that's usually what I think is happening. And one way to kind of look at or fix this is to do some degree of, I would say, tests. Like take a regular, do CV of a traditional system like Ruhex or ferrocyanide or something, and see if you're getting those same kinds of bubbles. Oftentimes you should not. But if you do, then it's probably an instrumentation or an electrode preparation problem. But if this is only happening in your catalytic system, this is, I think, probably due to microbubble formation, if I had to guess. So hopefully that was helpful. And yeah, I guess we will continue.
Yes. Okay,
Kind
so
of
we
going
had,
through.
yeah, I'm getting here. Ankush in Korea says, "How are we doing? Thanks for the live sessions.
Yeah,
Thanks for joining us. We
Thanks for
appreciate
joining.
it."
Yeah, absolutely.
Rashita Jain has a question. Is it necessary that the peak current we get in CV equal to chronoamperometry? No, not those are different phenomena. There's some similarities, for instance, but I'll try to explain a little bit, I guess.
Yeah.
And also, the follow-up question would be which current, because it's not constant, it's not staying the same. So, for instance, in a CV, when we get a peak, right, it's a result of a couple of things. We have this part here, that is kinetics, right? Which is from the Butler-Volmer equation, primarily. Okay, and then we have this part here, which is like a current decay, and so that's basically mass transport effect or impacts, basically, if you will, and that's from loosely speaking the Cottrell equation. Now, there's a lot here, which is why the question's a bit complicated, because with CV you have sweep rate, right? So the sweep rate will impact how high that peak is and where the interplay is on the current axis here, between the kinetics and the mass transport, which is why we get a peak. For chronoamperometry, we sort of have current here and we have time. And we get kind of the back half, if you will, you could think about it, of the mass transport part. So it's like a Cottrell response, but it's a different situation. We're not sweeping the voltage at all. We're applying some voltage, and then measuring the resultant current. So there's no guarantee, for example, that this starting current here will be equal to this peak current or something like that. The only thing you can sort of say is that and ideally this decay will be something like related to 1 over the square root of time.
I was talking about the initial, just a little comment. You said talking about the initial current of CA.
So again, the issue here is that the current decay will go according to the square root of time. But the issue with the initial current is a number of things. First is that the peak height of your CV, like I said, which you could call initial current in some sense, I guess, will depend on the sweep rate. With the chronoamperometry, it depends on how fast your instrument is measuring. Because when you say initial current here, this is what? Time equals 0? Well, you can't really measure. That's not possible. So it's like time equals 0.001 0.001 seconds, question mark. Like when, you know what I mean? If you could measure a split second before that, it would actually be a little higher. If your instrument could measure like the nanosecond that you're actually applying the current. So even that is a bit suspect in some sense. It's like the initial quote unquote current in your chronoamperogram isn't really going to, number one, be like super possible to measure like the instant you set, like the instant you apply a potential and the double layer sets up, and then you get the current decay or whatever. It's like it kind of depends on how fast your instrument can even measure that, first of all, and then that won't really have necessarily any connection or bearing with what the CV one like peak current is going to be, because that's a different situation when you're sweeping the potential. It's a whole different phenomenon, and like I said, that will depend on the sweep rate, and you're not sweeping in chronoamperometry. So it's kind of like, it almost feels like you're comparing apples to oranges, and as the phrase might be. It's like there isn't really, they both have the same pattern in terms of a decaying current, but like the peak, the start of it, almost there's not really a connection, I guess.
They are the currents are, it's like they're due to the same like underlying phenomenon, right? It's just like you have redox reactions occurring, you have double layer charging, you have stuff like that. But you're right. It's like in one, you have, in chronoamp you have a step potential, and then all at once you're charging the double layer, having Faradaic reactions occur, and then you're getting this decay. The potential that you decide to apply also matters in a chronoamperometry experiment, but because you're sweeping the potential, like some of the charge is already built up. And as you said, it's like the scan rate matters, all that type of stuff. So so it is different. It is necessarily different, and those two peaks, if you will, are not, there's no like mathematical, I mean, there is a mathematical relationship between them, but it's a relationship that nobody kind of cares about. It's a relationship that it's like you either do one or the other, and you get some information, but you never like look at the two or something. And they certainly don't have to be equal to each other. In fact, they almost certainly won't be equal to
I think
each
if
other.
they did happen to be, it would just be happenstance. It wouldn't, it would just be like, oh, they happen to be the same value, but I don't think it has any meaning per se.
Hope that clears it up, and
let us know if you have any follow-ups.
Talk more about it. Okay, so
I think there was some follow-up with the potassium intercalation. So you're saying negatrode is negative charge during negative. That's just the anode. The anode is during charging, it's a reduction reaction. So naturally, K plus is attracted. Again, that's the problem. Sure, K plus can be attracted because it's got a negative charge, but it'll be attracted in terms of like a double layer phenomenon. Like there's a negative charge on the anode, so to speak, and a positively charged solvated potassium cation will be drawn towards that just from electrostatic interaction. But intercalation is a bit of a different phenomenon. I'm not saying that's not happening. What I'm just saying is that there's a difference between like negative positive interaction that will happen because obviously opposite charges attract, and an actual electrochemical phenomenon occurring. I would need to read some literature and to believe that is a thing. Because again, if you're talking about K plus, plus an electron, like a reduction reaction for the K plus requires like 3 volts. You're not doing 3 volts here. You're an aqueous. So that's just my contention about it. But anyway, maybe the intercalation reaction is a possibility. But the oxyhydroxide's not layered material, I guess, to accommodate K plus. The oxyhydroxide form is an odd form. My experience working with like nickel oxide, nickel hydroxide, and nickel oxyhydroxide in alkaline system is that the oxyhydroxide is the I guess the other part of this too, which maybe is a side note, is that the oxyhydroxide is not going to exist very long at a reductive potential. So if your anode is reducing, you're probably not even, I don't know how you have the oxyhydroxide form. That's an oxidized form. It requires a positive potential. It's sort of, would that not be it feels like that'd be the discharging reaction anyway. So I'm not sure how the oxyhydroxide can exist at low or negative potentials. Basically, it usually requires an oxidation, and then the oxyhydroxide tends to be an electrocatalytically active species that will further catalyze other processes if you have them. In your case, you might not, because it's like just a supercapacitor. But if you have like some material that needs oxidizing or catalyzing or something, the oxyhydroxide form will do that. So anyway, we can sort of move on because we talked about that a little before, but I just thought I'd kind of cover here.
Yeah. Although it looks like he's talking about more, because he said he thought
the iron redox reaction could be dominant, but hydroxide negatively charged, which could be repelled during charging. So I think that there's absolutely some like thought that you're having about like attraction and or repulsion of electrostatics here. Like OH minus is in solution, K plus is in solution. You know, certainly solvated ions of that ions and cations are hanging around. They're everywhere. You got a 2 molar KOH, you got a lot of OH minuses around, you got a lot of K pluses. And depending on the charge, positively or negatively, let's just say, at either side at any moment in time, you will have one or the other attracted or repulsed. Just like based on, there's a positive charge here, so the positives will go away, the negatives will be brought towards it. All of that is like part of the capacitive situation, like the capacitance, the double layer capacitance, the supercapacitance, whatever. In my assumption, I suppose I'd say, none of that is Faradaic. Like none of those are Faradaic reactions. The fact that you have a positive charge at your electrode and a negatively charged hydroxide will be drawn towards it means that that there's going to be a redox reaction. Like that's a different thing. Hydroxide can undergo redox reactions, so perhaps that's more possible because there's a lot of reactions you can do with hydroxide in aqueous media. But potassium is the one that, again, I'm sort of getting hung up on because, like, again, negatively charged electrode, positively charged potassium can get attracted.
So then in that case, he's saying that iron redox reaction will be dominant for that very reason, right?
Because sure. Because potassium's not going to be.
Because potassium's not going to be.
That's fair. I think that's probably fair.
Yeah.
But again, the thing that I'm missing, just to be clear, Srinivasan, is that this intercalation reaction could very well be an explainable thing. I'm skeptical for the reasons that I've tried to explain, but it could very well be a possible, a very thing that happens. Like there could be some mechanism even at potentials under 3 volts, for instance, where potassium, I don't know, enters the lattice of the iron hydroxide somehow. Like that could be. I don't know. I'm not going to say that it's not happening. It just seems a little unlikely, just based on my knowledge of electrochemistry and like standard potentials of that that cation, I guess. And so I would also assume, along with you, that the iron redox is the dominating one, based on those assumptions. But I'm not going to fully say like definitely that's the case, just because, again, I would need to look into the literature to determine. And then the last thing I'll say, I guess, is just just because it's in the literature doesn't necessarily mean it's like perfect. I mean, people publish trying to be delicate, I guess, but people publish stuff all the time, and they're, sometimes they're theories, and sometimes they're like, well, this is what I think is happening, and then another paper comes out later that says, well, actually we've confirmed that this other thing is happening. Like that's part of science. It's actually, unless someone's being uh, disingenuous or lying about their data, I think a lot of times it's like, it's just the progression of science as in humanity, is that we learn something and we think something is a thing, and then later we sort of learn something else is happening. And so, it's possible that this is one instance where there's like an assumed process, and maybe you're calling that into question, and you're a scientist and you're perfectly allowed to do that. Is my my feeling. So hopefully that kind of wraps that up for you, I guess. Yeah. So
all right.
We'll move on a little here. Ankush.
Oh no, Ahmed.
Ahmed.
Ahmed,
Sorry.
Yeah, because we had to skip over him a little bit. Is asking, can you please any suitable method to remove oxide layer on aluminum electrode for corrosion experiments? I run several EIS in basic medium and get the same RCT in blank and in the presence of inhibitors.
Oh, that's tough. Aluminum is going to form an oxide layer, and there's like nothing you can do about it.
Yeah,
man. And I think that you're in base, which too is a problem. I think that acid will strip an oxide layer, but you're an alkaline, so you can't use acid if you're in base. You know what I mean? You can't like if you were maybe in salt solution, maybe you could add a little bit of acid. I think acid will like can remove rust. Like acid can remove, like just as a general thing, right? So it's like you could add, in a if you were doing brine solution, like just NaCl, you could maybe add a little bit of like hydrochloric acid, and maybe that would like remove it. And that's one of the things that people like when they bubble CO2, for example. You're probably not doing that because you're alkaline, but when people bubble CO2 in brine, like salt solution, it makes it slightly acidic, and it helps it corrode more because acidic will remove the oxide layer, the raw materials underneath there, and it'll corrode like crazy, which is good. You're trying to study it. You don't want it to corrode, but you're trying to study it, and then you put an inhibitor, etc. I mean, the only thing is electrochemically, in theory, you could
apply super negative
I guess.
super negative potentials.
Like you could like, I don't know if it'll just form immediately again, right? Like you could try applying, I don't even know what's the standard, like standard potential table. I don't know, like aluminum. I could just, we could look it up here really quickly, but like Al2O3 basically, right? That's not going to show up. Aluminum. Searching for Al in a page is not good.
Yeah.
But I'll get to the aluminum. All right, here we go. So aluminum, there's a bunch of them. So like aluminum, oh gosh, if it's aluminum,
so like
hydroxide, that's not the one. It'd be like aluminum oxide, which I know aluminum oxide is, I don't know if it's like actually aluminum oxide, because aluminum oxide is like ceramic material that's not electrochemically active. So actually, I don't know if it's like aluminum hydroxide. I can't quite find it. You might have to go to a fairly negative potential.
I'm getting one that like minus. It's like aluminum. It's a.
Is that the one? Aluminum.
It's a aluminum oxide plus
minus
water.
2. Oh, geez, if that's the one, that's a.
It's a 3 electron transfer process.
I don't know if that's. I feel like it would be aluminum hydroxide, maybe, and I didn't find it in this table.
Yeah.
I don't know.
Just pure aluminum hydroxide.
This might require a little more study. For the exact reaction that's occurring, or I would have to look into the literature a little bit to kind of find the right reaction for this oxide layer. But in theory, if you could apply a negative potential for a bit, that would reduce the surface. You might also cause other reactions to happen, which would be tricky because if you're going to really negative potential, you might be evolving hydrogen, you might be doing other stuff, and then it might be kind of tricky. You also might have to go more negative because you're at a positive pH, which means everything shifts more negative. So you're gonna have to go farther negative than you would normally because your pH is high. Everything shifts back with a positive pH. Otherwise, I can't think of anything else that would work because you're in alkaline, so acid won't work. If you can't do it electrochemically, I don't know how you would get rid of an oxide layer. I understand your problem. Like you're trying to say, hey, here's how aluminum corrodes. And then I add an inhibitor, it doesn't change. And it's like, well, that's because the aluminum itself is inhibiting because it has an oxide layer. And it's like, well, I'm not trying to prove that. I'm trying to prove how the native material corrodes. Can you do it in acid? I mean, is it, I guess that's my question. Like, what do you have to use basic medium? I would ask if you can use neutral or acidic medium and see if you're like, is there, maybe there's a reason why you're choosing base. I'm sure there probably is, but I would suggest if you can try to use salt or slightly acidic solution. I think it's possible you'll get better results, but there may be a good reason why you're forced to use basic solution. And so if that's the case, other than a reduction current to force the oxide layer away at whatever potential is appropriate, I honestly don't have any. I don't know. I'm not sure what you would do.
Yeah.
Yeah. So
yeah. Sorry, we can't be more helpful.
Yeah. But I mean, maybe that's a few things, hopefully one of those you can do. Ankush, I think, is next.
Yeah, Ankush in
Greg
Korea
has a question. We'll get to you, Greg, in just a second.
Yeah.
Ankush says, can you please give me some ideas about EIS measurements for supercapacitors? When I take nyquist plot at lower frequency values, the plot shows a lot of disturbance. Well, that's not surprising, even going to negative values. Also, can you please tell me about how to read bode plot for supercapacitors? Like, what are the inferences from the bode plot for supercapacitors in general? Okay. So let's think. How can I kind of show some of this? Maybe I can get a circuit. All right. So
I think one thing to also ask is when you say negative values, let's see. When you say negative values, you're talking about negative imaginary or quote positive imaginary impedance, or negative real impedance on the nyquist plot. So just a little bit of clarification with that would be helpful in addressing your question as well. So
I'm just getting a circuit simulation kind of ready to
and then
illustrate a little bit.
Also, we can kind of follow up on one question that you've asked at the bottom, which is what could be a possible reason for the disturbance in EIS measurement at low frequencies? Also, is there a difference between 2 and 3 electrode system devices? But when you have at low frequencies, because it's so slow, almost anything can be a disturbance. Because if you imagine, right, if you're at like 0.1 hertz, you need 10 times you need 10 seconds to do one cycle. What things can happen in 10 seconds? Well, actually, a lot of stuff can happen in 10 seconds. And imagine you have 0.01 hertz. It's like, all right, 100 seconds. Well, a lot of stuff can happen in 100 seconds from anywhere that can create instability in your system. So there's everything I would say in like the physical macroscopic world is moving on a fast enough time scale to cause disturbance in your measurement, which is one reason why it's very hard to make those types of measurements.
Yeah, run Kramer's Kronig on your EIS data as a general rule as well.
Yes.
Negative real impedance is a very bizarre phenomenon, and especially at low frequency. I would be very hesitant to ascribe any real meaning to that whatsoever. Kramer's Kronig may help you disregard those data. Maybe not the entire EIS set, but like at low frequency, if you have a lot of weird scatter and all these kinds of issues, you can do Kramer's Kronig. It will not fit. It will help you say, okay, forget about these points. Like you were just saying, I mean, low frequency is a nightmare.
Yeah,
as a general rule. As far as the interpretation of bode plots, supercapacitors could look like anything. Sometimes they look like this, which is like a Randall's circuit. Sometimes they just kind of look like a straight line like this. So this is I'm looking at the nyquist plot. So forget about the bode plot for a second. I know you asked about the bode plot. My point is sometimes they look like kind of like a straight line. Sometimes they look like a Randall's kind of a circuit. You might have that sometimes. But as far as the bode plot is concerned, for a pure capacitor, which is you're looking at a supercapacitor, like for a pure capacitor with a resistor, basically. I'll make the resistor kind of small just to illustrate my point. For basically a pure capacitor, on the bode plot, what you're looking for, of course, is just a straight line in the impedance magnitude. So the impedance magnitude of the bode plot is the red line here. It's just a straight line on a log scale. That's what a capacitor looks like. For a perfect capacitance or perfect capacitor, what you're looking for is a phase angle of minus 90 degrees. Okay, so this is like the most basic possible thing. If it's slightly non-ideal on the Nyquist plot, the angle will start to go down, and the phase angle will drop. So basically, if this is like my phase angle graph is at minus 90 degrees, it's like a perfect capacitor. If it's minus 80 degrees, it's a less than perfect capacitor. It's like a non-ideal capacitor. So that's some of the things in the bode plot. Now, when it comes to something a little more complicated, like if you do have a Randall's, I don't know, behavior for your supercapacitor, I mean, you have some Faradaic reaction of some sort, I guess, occurring. What you're looking for, so if I have no Randall's reaction kind of whatsoever, what you'll see is just kind of like the capacitor like I showed before, right? If you do have a Randall's charge transfer reaction, what you're going to see is the phase angle kind of has an inflection, basically. Either you'll see like a peak. See, there's kind of like a peak, like the downward peak on the blue plot here. So go away. So see the blue, you'll have a downward peak or like an inflection. So it goes up and then back down again. Peaks are hard to sort of talk about with a bode plot. We don't really think about bode plots with peaks. We look at the peaks on Nyquist plot with like a semicircle or something like that. But when you look at the bode plot, for instance, you can look at the inflection change on the phase angle. So one of the things that you can look for instance, is when does the phase angle kind of change or invert itself. That can be an indication of a Faradaic process in addition to the capacitant behavior. And in this case, it's more like a double layer. But if I have capacitor, you can see that in this case, let me drop the low frequency a little bit just to kind of show you at the low frequencies. You're probably not able to get this far, but this is 1 millihertz and you're talking about noise at low frequency. So if I have a capacitor, eventually the phase angle will basically settle at minus 90 degrees. So you can see that I have this kind of big peak here, down and then up in the bode plot, which is from my sort of my redox reaction. If I make that redox reaction start to go away, it's like all capacitive kind of. But eventually at enough of a low frequency, I start to get to the capacitance, which is mainly what I'm after if I'm looking at a supercapacitor. If I have some non-ideal capacitance or it's diffusional stuff, like in this case with a Randall's element, it's mostly diffusion. The bode plot will end up at about minus 45 degrees. And so what you're looking for in the bode plot, I guess you could say, is that where is the phase angle kind of trending towards at low frequencies? Now, if you have scattered plots and all kind of nonsense, you got to cut your data off where it's still good, something like that. But one of the things you can look for instance, is when does the bode plot impedance magnitude start to kind of look like a straight line, basically on a log scale? That's an indication where it's mostly capacitive. And then what is the phase angle going towards? Is it going towards minus 90 degrees or close to minus 90 degrees? That's kind of pointing towards capacitance. If not, it's sort of non-ideal or it's mass transfer or something like that. So I hope there's a few little tidbits there just to kind of talk through what you're looking at in a bode plot. Ankush, you can follow up if you have anything else. Let's see. There's a few comments. I even tried to reduce the points per decade, but still could not solve this issue of negative real impedance. Yeah. You can try increasing the amplitude. Sometimes the resolution will be poor at low frequency because as you go down in frequency, the impedance goes up. As the impedance goes up, the current response goes down. And as the current response goes down, it becomes more difficult for the potentiostat to measure. Right? It's like if you're measuring microamps with an impedance, and then your impedance goes up by 3 orders of magnitude, now you're measuring nanoamps. And then if it goes up 2 orders of magnitude, you're measuring picoamps. Like you start to the measurement becomes difficult. So if you increase the amplitude, you'll induce a greater response and you might be able to clean up the signal. But of course, if you have a high amplitude at the high frequencies, it could get crazy. So you'll have to find a balancing point, but you might try, for example, increasing your amplitude a little bit at a time and see if you improve the resolution, particularly at low frequencies. You can try that. I have tried Kramer's code and I get a good chi value if I remove the lower frequency. Yeah, I'm not surprised. you can try some of those things that I mentioned, and then ultimately you might be stuck into a conclusion that I can't get good low frequency data. Unfortunately, that might be, sometimes that's just where we're at. Like low frequency data is not always possible for a variety of reasons. It drifts around and stuff. So, okay, hopefully that kind of covers a lot of what you were asking about there. So
Yeah, I think the only last thing to mention just before we'll get to Greg's question. In a
right,
minute.
3 and 2.
Yeah, just 3 and 2.
Mhm.
So yeah, there are differences between doing EIS in a 3 electrode or a 2 electrode configuration. The main difference, and we can go into it in more detail later if you want to. We're just trying to get through all the questions. Is that in a 3 electrode configuration, you're primarily looking at just one electrode. You're just looking at the working electrode. In a 2 electrode configuration, the EIS consists of both working and counter, or just contributions from both electrodes. And just, I guess, briefly, the reason why in a 3 electrode you only get one is because you typically are reporting potentials or voltages with respect to a reference electrode. And so when the impedance is calculated and you're looking at voltage over current, the voltage is only the voltage of working versus reference, and the current is the same throughout the entire electrochemical system. So there are contributions only in the phase a little bit from the counter electrode, but the voltage that's being used to measure is just from one electrode, which is the working. As opposed to a 2 electrode configuration where the voltage is between the two of them. So as they move and as they change, you're getting contributions from both. All right, so
Yes.
with that said, let's get to Greg's question. Greg Alston is asking, how does the density of the electrolyte in a lead storage battery change when it is discharged? I need to know this.
So in a
Yes.
lead, so I assume you mean like a lead acid
Yeah.
battery, I assume.
Yeah, I think so.
I had to kind of remind myself about this one.
Yeah, I forgot
So
about glass batteries.
if this is accurate, which I believe it is, it's not one that I like keep on my mind, I suppose you'd say. This is the one. No, it's just the Wikipedia page for lead acid battery. So, so during discharge of a lead acid battery, the total reaction is this. So if this is the one that you're referring to, I won't highlight it in blue so you can actually see it. Oh, good Lord.
Oh,
I
heaven.
zoomed in way too far, too fast. Okay. This is the discharge reaction. Okay. So if this is the reaction of interest that you're referring to, that I assume when you say lead storage, my assumption is that the density of the electrolyte will decrease as it's discharged. The reason is that the discharging reaction involves the consuming of sulfuric acid in the electrolyte and the production of water, and the
And the sulfate binds to the
sulfate.
to the
Yeah,
lead.
basically the discharging of the battery involves grabbing sulfuric acid out of the solution and binding it to lead to make lead sulfate. But this is one of the problems with lead acid batteries. They slowly lose over time because one of these don't go back very easily, right? It's either this one or this one, like doesn't get stuck. It's kind of insoluble and stuff like that. So, or not very electroactive. And so lead acid batteries, this happens. Anyway, the density of sulfuric acid is greater than the density of water. The density of sulfuric acid, depending on the concentration, is like 1.5 to 1.8 grams per milliliter. The density of water by itself is 1 gram per milliliter, roughly at room temperature. So as the more dense thing gets eaten up, the density of the electrolyte will probably go down as it's discharged. So that's my answer.
Yeah. And then Greg Alston's next question is, why is alternating current AC used for measuring the resistance of an electrolytic solution? He wants to know the answer to this too.
This one too?
Yeah, this one too.
Okay. Thank you for clarifying.
Yeah.
It's used.
Oh, do you want to get into the impedance? Just
well, I
impedance of
mean,
an AC
it's
circuit?
sort of like, why is it used for this? Well, it's used for getting the resistance of anything.
Yeah.
It's fundamentally impedance is a measurement that allows you to probe resistance, capacitance, all sorts of things by modulating the frequency. So one of the reasons that it's really useful is that it's non-invasive because it allows you to perturb the system with a very low amplitude. So you're sending a sine wave into the battery, or the, I assume we're still talking about the lead acid battery, but whatever the system is.
Yeah.
Um,
Or electrolytic solution in this case. So it's
yeah, exactly. So this is just like the leading resistor. So
yeah, just a leading resistor.
So if you have a lead acid battery, or any battery, I suppose, but in this case, yeah, sure, lead acid battery, right? You have anode over here. I'll just make it more general. It doesn't have to be like specific to lead acid. You have an anode over here. You have your cathode over here, and you have electrolyte in between, right? There's circuitry we can sort of draw on this, and let's just say like I might have like some reaction taking place on this side. So this is like a resistor capacitor in parallel. So some Faradaic reaction. Same thing on this side. I might have cathodic reaction occurring, and then I have resistance in my electrolyte. So I could draw a circuit something like this. And so the reality is like, okay, well, I want to measure just this resistor, right? Just this is the resistor. We sometimes call this R ohm or R0 or RS. I mean, there's a bunch of names for this. I'm trying to measure this. The reality is that impedance allows us to measure this because it typically is probed at high frequency. So like when we look at a Nyquist plot, for example, of like a battery, we get something like, you might get something like this. And so this would be like the anode, this reaction. This would be the cathode reaction. That's just 1,000 circles on my screen. But if this is the origin here, this intercept here, that right there, that's the ohmic resistance. So we can measure it with impedance. It's one of these benefits of doing impedance is that at high frequency, effectively, it's like a whole nother discussion. I have a lot of talk about this in my webinar, so I'm trying not to talk about this forever because there's a bunch of questions. But at high frequency, the impedance of capacitors is basically zero. So the pathway for current or measurement at high frequency, so in impedance, that's a G, I promise.
Mm-hmm.
Oh God, no, I ruined it. High frequency. I cannot write.
Yeah, it's all good.
It's pretty hard. At high frequency, the pathway is something like this. It goes through these capacitors that have basically zero impedance, and so I'm just measuring this right here, which is what this intercept is. So impedance is really helpful for doing that. I talk about a lot of this in some of my impedance webinars on our YouTube channel. I would encourage you to look at those. I kind of go through that in a little more detail in terms of why the impedance is bigger or smaller under certain circumstances. But hopefully that kind of talks a little bit about why impedance is used to measure specific stuff like the electrolyte resistance.
All right. Okay, moving on. Shumali Hassan 7476 says, I am doing DPV for sensing azithromycin using MoS modified GCE, where I don't get any peak at low concentration, but at large concentrations, such as 300 micromolar, peaks appear. This problem is in my material. Yeah, I guess I don't know what the low concentration is, but it's like, okay, if you're getting azithromycin at a larger concentration, 300 micromolar,
it just looks like you're hitting the detection limit.
yeah, I mean,
this is just the detection limit thing, is it not?
It could be. Another thing that you can do in DPV is increase the amplitude of the applied signal. So if you're not getting anything, one thing that will overall increase your signal, period, is just increasing the amplitude of your DPV experiment. So even though you want to, ideally get a nice kind of tight peak in DPV, if you're not seeing anything when the concentration gets too low, I would say the only other experimental parameter that you should play with is something like increasing the amplitude. That could be one thing, depending on what the parameters are. But yeah, it might be. Yeah, you might be running into the limit of detection. Make sure that your potentiostat settings are for like low current. You might have to use a Faraday cage, possibly, but without seeing the results, I'm not 100% sure what could be causing the issue. So, but if you give us some more details, maybe we can work it out. But hopefully that helps. That's at least a I don't want to say it's exactly your material, because your material is able to, it looks like it's able to detect something, 300 micromolar. But I guess you should also test it with and without your material. Like, try DPV 300 micromolar without your material, see if you detect it, then add your material, see if you also detect it, and then try just GCE at a lower concentration and see if you see something. That would be those would be kind of the initial tests that I would consider when seeing whether or not your MoS is appropriate for azithromycin detection. So hopefully that was helpful. Let us know if you have any further questions. All right. Okay. So next question. All right. Suyuma Bebe 2856 is asking, hi everyone, in electrochemical energy storage, when molybdenum sulfide is combined with other oxides, carbon-based materials, or sulfide selenides as composite heterostructures, its performance is significantly enhanced. What electronic properties of molybdenum sulfide are changed in these combinations, since molybdenum sulfide stores energy mainly through redox reactions and ion intercalation? Can these changes be studied electrochemically? Thank you.
Yes. Next question. No.
Yeah.
So the main reason is the conductivity. Molybdenum sulfide has a really poor conductivity. So when you add carbon-based materials, in particular, I don't know, sulfides, selenides, and or other oxides, probably accomplish some of the same kinds of things. But one of the main reasons why you have to add graphite or carbon of some kind to something like MoS₂ is because one of the main drawbacks of molybdenum sulfide is that it has low intrinsic electronic conductivity. So its performance is enhanced because by itself it will conduct very poorly, which means that even though it ought to, in theory, intercalate lithium quite well, which it does, and it has a pretty high theoretical capacity, it will not do so very well because electrons aren't getting there. They don't move very easily. It's not a great conductor. So when you add carbon, you can kind of think of it as like, I have this material and electrons are just kind of like walking through mud. They're sludge. They can't move very easily. And you add some carbon in there and the carbon's like, hey, come with me. I'll shuttle you across this vast plain of molybdenum sulfide. And then I'll bring you right to the surface where you can intercalate lithium and be super happy. And that's exactly what happens. It's like the Lucan capillary school children phenomenon. That's exactly what happens. So yeah, I mean, that's really it. It doesn't actually change the electronic properties of molybdenum sulfide, but it improves the performance because it imparts electronic conductivity, right? The problem, of course, the problems can come from the fact that you're trying to, you have to cut your material, your primary material, that's a hard word to say, molybdenum sulfide with something else. And so now some of your mass is taken up by something like carbon, which actually can act as its own material and can intercalate lithium in some ways, depending on which form of graphite you're using. But mainly it's just there to impart conductivity, and it's taking away from mass that would otherwise go to the anode. So that's part of it. Can these changes be studied electrochemically? Yeah, of course. I mean, you by the addition of graphite, you're going to get a thicker SEI layer, but you're going to be able to allow the molybdenum sulfide to reversibly, hopefully, intercalate and deintercalate ions to study its redox reaction. Whereas when you have it by itself, unless your loading is very, very small, like very few milligrams per centimeter squared, if you have any kind of layer of MoS₂, its lack of conductivity will severely hinder its performance. So that's really, I mean, I think that's kind of mainly the answer. If you cut it with other oxides or other materials, you're probably just using some kind of a amalgam's the wrong word because that's like mercury, but some combination, some mixture of materials to take advantage of the properties of all of them. Like you'll have some sulfide, some selenide, some other oxide that itself is more conductive and also does its own redox reactions, its own charge storage mechanisms. Then you'll have some sort of composite material where you have intercalation of lithium and the MoS₂. You have, a conversion reaction or an alloying reaction with this other material, this selenide, whatever. You'll have a lot of stuff happening and you get some composite results. But all of that is electrochemically can be studied electrochemically for sure. Follow up if you have any more questions about that. But I think the main sticking point is that it's an electrical conductivity problem with MoS₂. A lot of alternative anode materials, I guess I would say, suffer from this problem. Magnitudes are better in the edge plane direction, interestingly. So yeah, okay, yeah. Versus of Gold says, I guess one plane is poor conductivity and the other one. So I guess that would suggest that if you can get just, I guess, edge plane MoS₂, it would behave a little better. So that would suggest that. Maybe that's difficult to make. I'm not really sure, to be honest. But electrical conductivity is definitely a problem with a lot of anodes, and this is one of them. So,
all right. Next question. Chandana Yak 3366 is asking, I have calculated ECSA from CV and then normalized the polarization curve by the ECSA.
Mhm.
I found that the current density normalized by ECSA is following inverse trend polarization curve for HER earlier. How is this possible? Why is this happening? Does that mean intrinsic catalytic activity is not good? That's why by normalizing trend reverse. So let's see if we can kind of need to
following
unpack
the
this.
inverse trend polarization.
Inverse trend polarization curve. Inverse trend polarization curve. I don't know what that means.
So I guess I don't understand. So it sounds like what you're doing is you got a bunch of polarization curves like LSVs or something, studying the HER right?
Reaction.
And it's what you're saying is that you're normalizing by the ECSA, but it sounds like what you're doing is you're getting a different ECSA for each one. Because if you're finding that like as you normalize, the trend is changing, it sounds like what you're doing is you're assuming the ECSA is constantly different every single time. Because if you just get like, if you have like a bunch of curves, right? You have like this curve and this curve and this curve and this curve, and you have like I and E values, and then you normalize the current by the ECSA for all of those curves. Well, they're all going to be the same trend because they're all like every current is just divided by 0.017314. Like you're just dividing every current by the same number. So the trend, nothing will change. But if what you're doing is in each of those CVs, you're assuming the ECSA is different by whatever mechanism you're using to calculate it, which I suppose would be like the 210 microcoulombs kind of, phenomenon in the HER region or something like that. Then anyway, that's what I assume you're doing, which would explain. Yeah, calculate it. Yes. Okay. So he says yes. So it's like you're doing like double duty, which is to say you're doing the like hydrogen butterfly peaks or something of that nature,
Mhm.
right? Something like that. And you're
Yeah.
getting the area under the curve basically, and finding, I mean, one quick answer would be that your material is deactivating over time. I don't know. Like if you're doing this like over time, if it's a time um, variant thing, something like that, right? Um, you might be like, just the ECSA is going down over time, um, or whatever that it's getting worse. Like if your trend is reversing, it's getting worse as you normalize it. Um, then your material could be just deactivating, like getting worse. Like it. I mean, this is normal. Like catalysts won't behave perfectly forever. Like there's some shelf life to it or something like that. So that's one possibility. I guess the other tricky thing is just the ECSA calculation is normally a pretty meticulous one. Like for like the most famous one, that whether you're doing it this way exactly, I'm not sure if you said, you didn't say exactly what you like. If you're using platinum, it's the 210 microcoulomb kind of thing. Um, uh, each material has a different ECSA.
Oh.
LSV for HER have different samples. Okay, so it's like you're saying you have different samples and they have different ECSA.
And it's the same. It's the same like LSV scan rate basically.
I would assume it's the same parameters. Current density normalized,
Correct.
following inverse trend polarization curve. Well, then maybe the answer is okay. So when you're saying it's following the inverse trend, also,
Yeah. What does that mean?
I assume you mean normalizing by ECSA, not geometric. Yeah, right. I understand that.
Yeah,
That's a
that
wise
makes
thing to
sense.
do if you can calculate ECSA, which it seems like you're doing. I guess I would also ask, when you say it's reversing the trend, do you mean like by sample 1, 2, 3, 4, I had like sample 1 was the best, sample 4 was the worst, or something like that, just on non-normalized current. And then when I normalize it by ECSA, I get the opposite. So by trend, you mean like the normalized by ECSA is showing me that my like current density is best on the sample 4 instead of sample 1. I think that's what you're meaning by it. If that's what if that is what you mean. If that's the case, if it's just that like by normalizing by EC, okay.
Okay.
So I actually don't think you have a problem here. I think that you're just discovering that the material that looks worse is actually not. I don't think there's anything going on here. I think that um, uh, what this means, for example, is that like let's say the material has that without normalized current, without normalized, right? That was the best, right? It had the highest current, like raw milliamps or whatever, right? So
Mhm.
you said that was number one. That's the best one. Well, what you're finding out is that the reason that it had the highest current is because it has a huge ECSA,
Yeah.
right? So what that means is that it has a huge surface area. And that's why you're getting more current. So there's two ways of looking at this. One is that the material's fine and it just has a really high surface area. And so when you normalize it, it's like it looks less, but it's like, well, it depends on how much mass, like the mass is the other part of this, right? Of course, it's like if it has a huge surface area and it's like a nanogram, well, that's excellent, right? That's great. I only need a small, tiny little mass to get this huge surface area. If it's a huge amount, if it's like a kilogram, that's terrible news. It's like you want to, that's the specific area by mass. That's another factor that plays a role into this. But one of two things is true. Either you're just finding out that your material has a really high surface area. Okay. And as a result, the reason that you got a high current was because it has a lot of surface area. So that's fine, right? It's normal. And the other
Mhm.
material got a lower current because it had a lower surface area. Like you're just finding that out. And the other way to look at this is that the material that you thought was bad is good because it only got the lowest current but it still got all that current from a really low surface area. It's like this material only needs 1 square picometer to give you a milliamp. And the other one gave you 10 milliamps, but you had to put a ton of it in there, right? It's like if I'm going to punch Alex, right? I'm going to beat him up and I punch him 57,000 times and then I knock him unconscious. And I'm like, I did it. And then he looks at me and he just taps me with 1 finger and I immediately fall and I collapse. Well, we both had the same effect on each other. We both got knocked unconscious, but his was much easier and did much less work. So he's like, he's got all, he is like less surface area was required. He is a tiny finger, tiny surface area. Maybe that's a weird analogy. I don't know. I'm trying to think of something in real life that I can compare this to.
The 1-inch punch.
1-inch punch, exactly. Yeah. That's kind of my idea. Yeah. So anyway, maybe that kind of makes sense. Maybe it's a little bit hard to wrap your head around. But I don't actually think you're finding a problem. I think you're actually just learning fundamental things about your materials. Is that if your material gets you a ton of current out of a small amount of area, maybe it's great, right? And maybe your material that has a tremendous surface area, if you just add more mass to it, it's going to give you more results because it has a huge surface area. Or maybe that's bad because for all that surface area, it's still only getting you this much current. And that's not great. So maybe the material's not that good. It's like, it's great that it has a high surface area, but it's bad because it's only giving you, a small amount of current for all that surface area. And that's not great. Okay. Yeah. So, okay, you got it. I'll stop talking. Just remember, you knocked somebody out. That's what.
Right.
That's the takeaway.
All right. We have another question from Shumali Asan 7476. Can you tell me how to make a redox probe of ferro? Like we have to use both ferrous salt, or should I go for any one of them? Should I use both salt of ferro to make a redox probe, or only use one of them? So, the way I think about this, we rarely use. Sometimes how we use the word redox probe can be a little bit ambiguous. I think about this a little bit like making a reference electrode. So you can create a potential in in an electrochemical system in a reference electrode by just having like a piece of wire, like a platinum wire or silver wire or something. And then when you add a mixture of the ferri and ferro cyanides or something, iron 2 plus iron 3 plus mixture, you can govern the potential of that electrode based on the Nernst equation. So when you add both of them into it, the ratio of their concentrations will allow you to kind of peg the potential of that electrode, and hence your quote redox probe. And it's just based on the Nernst equation, and I'll just bring that up just so that you can see it. Where is my? Here we go. So, if you're here, and you have your oxidized and have your reduced form. So all you need to do is just change this value, and you'll change the potential of your redox probe. So it's better to add, not just one or the other. I think it's generally better to add both. And if you add 50-50 of both, then your potential will be pegged at the E naught because the natural log of 1 is 0, and your E and E naught will be the same. But you can always change this. And remember, it's natural log, so you need like a 10-fold difference in the activity of these to get just a 59, 60 millivolt difference between them. So just keep that in mind as you create your redox probe. But hopefully that helps, that answers the question. If you need more information about, like, say, the construction of it or something like that, let me know. Because you have a lot of questions.
Yeah, okay. We sure do.
Let's see. Kalpanasalam 5392 is asking which polymers we can use as supercapacitor electrodes other than PANI.
Polyaniline, I think.
Oh, polyaniline?
I think so.
I don't know. Do you know?
I don't.
I don't. Okay.
Polypyrrole?
Pyropyrrole. Yeah.
Maybe.
Maybe find some imidazolium stuff. I'm not really so sure.
Yeah.
I don't work with.
Not all polymers are electrically conductive. Right?
Correct.
It's a tricky thing.
Oh yeah.
Some of them you can kind of back to the molybdenum sulfide kind of thing. You can impart sometimes conductivity to some polymers by putting graphite in them. They'll sort of mildly conduct or whatever. But I don't have a ton of experience with electroactive polymers. Basically, I did a very short collaboration when I was in graduate school with a group. I think I used polypyrrole and polyaniline actually, very briefly. It didn't go anywhere. I didn't learn a lot. All I know is that those are things that you can do. That's kind of it. It was a very short kind of thing, and we were looking at a bit of redox something or other, and it kind of fizzled. It was, these things happen in grad school. It's like, your advisor and his buddy are kind of like, hey, what if we did a thing? Go do it. And you're like, I don't really know if it's working. They're like, whatever, forget it. We'll do something else. So that was the extent of my work with polypyrrole or polyaniline or maybe there might have been one more, but I don't have a ton of polymer knowledge. So sorry, I'm not really sure.
Yeah. Sorry about that. Let's see. Draco Gaming official 23 is asking, the salt bridge in a galvanic cell is made up of question mark.
A paper towel.
Talking
about a Daniel cell, basically.
Yeah, it could be a Daniel cell or something along those lines. But it just needs to be a conductive electrolyte. It depends on what the galvanic cell is. Ideally, it can be, it can just be like a tube that connects both sides that contains the same underlying electrolyte. So in the Daniel cell, it was some kind of sulfate ion. So it was either copper sulfate or zinc sulfate, and sulfate ion needed to be in the salt bridge. And eventually, the constituents of the salt bridge will kind of move back and forth, but it takes a while for them to diffuse. So no matter what is in either cell, you should have, I think it's important to have a similar anion or cation. But yeah, just made up of the underlying electrolyte. Okay. Ferris is asking, how significant is the electrostatic force when thinking about ions being attracted to either electrode? Can it actually pull the ions into a gradient, or will other phenomena overpower that? So I believe that the electrostatic force is significant at pulling ions or attracting ions into the electrode. That's ultimately what causes the potential difference. Like the potential is just actually it's almost changed how I think a little bit more about how we describe electrochemistry, but that electrostatic force is very narrow. At an electrode surface, like it's the double layer basically, and that only it doesn't extend that far out into the solution. So it pulls ion. In fact, it necessarily has to pull ions to maintain the potential. Like if the voltage or the potential of your electrode is large, and it's only large to create, any negative charge that's being built up on the working electrode, you need to attract like an equal and opposite amount of positive charge from the solution to create that voltage. And that's an electrostatic force. and that is literally pulling ions from the solution to counterbalance that that charge. And the primary force is electrostatic in nature. Um, so yeah, like are there other phenomena that can overpower that? I'm not so sure if there's other phenomena. Even, I think this stuff even exists in, like, monolayers and stuff like that. I heard a really interesting story. Um, Someone did an experiment where they had an electrochemical cell, they formed a double layer, and then they actually picked the electrode up out of solution. They didn't rinse it, and then they put it in a high vacuum system to measure work functions. And the double layer was still present. So, like,
Even when they pulled it out of solution?
they pulled it out of solution
How's that possible?
with their hands.
Oh, they used their hands.
They used their hands.
Okay.
I don't know, but when they removed the electrode out of solution, the double layer still existed. They didn't, like, dry it off or anything or rinse it. They just moved it out of solution into a high vacuum system, and the double layer, because it's really compact, like, all the liquid hasn't like evaporated, um, and that potential was actually maintained. The electrostatics kept it together, and they made some very interesting, experiments with that. So it's actually pretty powerful. It's a surprisingly powerful thing. But anyway, I hope that kind of answers your question a little bit, Ferris, or at least provides some insight. I can't think of any other forces, sort of say, that play a role in that. Okay. All right, we talked about this. Draco Gaming official 23 also asks, a cell is set up with a 0.1 molar hydrochloric acid on one side and 0.1 molar acetic acid on the other side, both with 1 atmosphere of hydrogen gas and platinum electrode. Explain why the electric field of the cell is not 0, and what
EMF.
and what is this electrochemistry of chemistry honors? Well, it's not. So, but yeah, this is I know it looks like it's a test question, but it's actually very simple, because this is the equivalent of putting 2 reference electrodes in solution next to each other, measuring the open circuit potential between them. And acetic, hydrochloric acid is a strong acid. It dissociates completely, and you're looking at the concentration or activity of protons in that solution. For a weak acid like acetic acid, even though it's 0.1 molar, it's not going to completely dissociate. So the concentration of protons on that side of the electrode is going to be smaller. It's going to be different. And so, because those two things are different, you have these 2 different activities or concentrations. You're literally looking at, share my screen. You're looking again at the Nernst equation, and specifically, you're looking at the Nernst equation for your SHE. Let's see, two protons plus 2 electrons gives you H2. Right? You're just looking at this reaction, and in both sides, these are not equal to each other, right? The hydrochloric acid situation and the acetic acid situation are not the same. And so, because they're not the same, the activity in this reaction, when you're putting, reduced and oxidized together, even though you have 1 atmosphere, right? Both of them have 1 atmosphere. Well, concentrations of protons are different. So that's why you're going to measure a difference in the potential. So hopefully that answers your question. We have a lot of questions, so I'm trying to get through things relatively quickly, but hopefully that answers it. Where
are we at here?
Where are we at? I have one from Life of Fart, 3189. How lithium battery charge?
I can show you how that works.
Yeah.
Sure.
Sure.
How does a lithium battery charge? Carefully,
Carefully.
slowly, methodically. That's the dad joke answer.
Yeah.
So I'll draw a typical lithium-ion battery. That's a B. Writing is very difficult.
Mhm.
So lithium-ion battery for the anode, you'll have something like carbon, graphite. For the cathode, let's just say something like lithium cobalt oxide, the famous classic example. They don't use this one anymore totally. When it is charging, so for charging, at the anode, we have Li plus an electron plus 6 carbons gives me LiC6. At the cathode, we have LiCO02 goes to Li plus electron plus COO2. So during charging, lithium is going into the anode, leaving the cathode. During discharging, it's the opposite. Okay, so LiC6 breaks apart to Li plus an electron plus 6 carbon, or C6, you could draw it either way. And the cathode is gaining lithium. So CO2 plus electron plus lithium plus gives me LiCO02. So in other words, the charging of a lithium-ion battery involves lithium ions entering the anode by a reduction reaction. And the discharging is where they give it up. So the anode is oxidizing. So we sort of call anode and cathode by convention as the sides where the anode is the side where there's an oxidation reaction when it's just during discharge that we classify it. So that's why it's called the anode, because during discharge it's oxidizing, and the cathode is where the reduction is occurring. So during discharge, the cathode is as a reduction reaction, which is the addition of lithium basically into the lattice. So that's really it. I mean, ultimately you can see that a lithium-ion battery is passing lithium ions back and forth between the anode and cathode. That's basically what it's just a game of ping pong of lithium ions, ultimately. So that's the reaction. I don't know if that's exactly how it happens. There's a lot of answers for how precisely, like more mechanism kind of answers, but those are the stoichiometry, the reactions for a typical lithium-ion battery. And most other materials that are anodes or cathodes have a similar, the reactions will be slightly different, or the amount of electrons or what have you be different, but that's the same fundamental idea about how a battery works.
All right. So palm mining has a long list of questions. I think they're all kind of related, but all related to zinc-ion batteries. So it says there is a growing research interest in self-charging zinc-ion batteries that can autonomously recharge by interacting with ambient air. At the same time, zinc-air batteries are a well-established class of zinc-based systems that rely on oxygen from the air for their charge-discharge reactions. Could you explain the fundamental differences between self-charging zinc-ion batteries and the conventional, zinc-air batteries? In particular, please describe the redox reactions occurring at each electrode during charging and discharging of the zinc-air battery, self-charging, and the charge-discharge of the air rechargeable self-charging zinc-ion battery.
It's a lot of the word charging.
It's a lot of the word charging with zinc and air and ambient, and
Yes.
they sound very similar, if not the same, but maybe they are different. Do you know anything about this?
Yeah, so I mean, I'm looking a little at it. To be honest, I'm not really an expert on zinc-air batteries at all. I was not aware of this self-recharging phenomenon. I just found a few papers to kind of look a little at it and kind of learn as much as I can tell in a very quick time, obviously here. As far as I can tell, I mean, some of the main differences are that the self-charging zinc-air batteries, it's a cool phenomenon because you can expose it to air and or pure oxygen, and it will over time recharge, but it's very slow. And so I think part of the problem with those is that because it's so sluggish, it can take hours and hours and hours if you wait for it to recharge itself, basically. And so it's not ideal, to say the least, to sort of wait for the oxygen to naturally do its thing. So, we can apply basically a positive potential to our battery and charge it up manually, or what have you. So as far as the reactions, honestly, I mean, I could just show you the Wikipedia page here, which isn't going to help you. It's kind of like you could also look at Wikipedia here. I don't have a lot of experience with zinc as I do with lithium, or even a little knowledge of sodium. It's a similar phenomenon to lithium. But a zinc-air battery, even just looking at it, it's kind of interesting because, like, as far as I can tell, the cathode reaction involves oxygen gas during discharge. So I'm actually not even sure how the self-charging would work, because oxygen would be a product in a charging reaction if this is the same, but maybe it's a different reaction. But it's like, if you're getting oxygen, that it's the opposite. I would expect oxygen to be discharged during, that's the wrong word. I would expect oxygen to be released during the charging, because I believe that the cathode consumes oxygen during the discharge. So I guess I don't even understand how a self-charging would work by having oxygen present. I would assume that would more discharge it than charge it. So I clearly don't understand anything, and I should probably just leave the question where it is. I'm very sorry, Paul Manning. I don't know enough to answer this question. It's a really great question. And I don't know enough to be able to answer it.
Sorry.
Yeah. Yeah. Sorry. I know I'm the battery guy here, and I'm going to have to let you down because I don't know enough about zinc-air, and the self-charging thing is a cool phenomenon. I'd have to read about it.
Yeah. All right. Next, Tamra 6793 is asked, do you do protein electrode?
Only on Tuesdays.
Only on Tuesday. I don't know what a protein. I mean, you can put proteins on electrodes. There's a whole bioelectrochemistry field, but a protein electrode
as an electrode by itself, I doubt that would work.
Yeah,
proteins aren't like don't have conductivity enough.
No, I mean, they may have a redox center somewhere in the protein,
but I doubt it would work as an electrode by itself. That seems unusual.
Yeah, I'm sorry. We don't know enough about protein and electrodes and bioelectrochemistry. So we're sorry about that. Okay, we have a few more minutes. We're gonna try to get through this. I'm just gonna say, might not be able to answer all the questions. Just gonna do
the best we can.
Let you know.
Okay, a lot of these are Chandan's follow-up, so hopefully we'll get.
Yeah.
Is it Zarkam?
Yes.
Okay, so Zarkam says, I plot a graph between scan rate versus anodic and cathodic currents. Okay, and the slope calculated using linear fit model, and exponential is different. For example, linear 0.11 and exponential 0.7, which is better. 0.7 as an exponent, is that in?
That's in the
Linda-Sevcik equation? No, that's not right. What's it in?
The 0.7 is if you just take a CV and you just look at the any current as a function of the scan rate, and you're looking at like the Dunn pseudocapacitance.
Oh, is that where
the Dunn method for pseudocapacitance? Then actually, it's funny. 0.7 is kind of smack in the middle of it. It's like that. It's like an impedance. If the alpha,
it's halfway between mass transport and capacitance.
Yeah, and in this case, it's halfway between Faradaic and capacitance, because 0.5 for the exponential is closer to the it's closer to like the Randall-Sevcik 0.5 square root dependence on peak current, and then 1 is similar to capacitance having a linear relationship on the scan rate.
Mhm.
So
But in general, it sounds like if you're getting a 0.7 um, fit like parameter, that's in line with the Dunn. Was it the Dunn
yeah, I think
Dunn
the
method?
Dunn method.
So
Bruce Dunn.
in general, as an answer to your question, I would assume that this is in line with the Dunn method for your CDL calculation. That this 0.7 sounds reasonable for, I guess, probably pseudocapacitance of some kind here, so something like that. Because you said it's, I mean, it's like it's not right. Is it?
So I guess one question is, it's like he says he's using a linear fit model and an exponential. And so I guess my question, or more comment really is, if we go, let's see if we go here.
I have this Dunn Trissetti paper that's like differential capacitance. I covered this in one of our live streams like a year ago. I remember doing this. Oh, I just have, this is like some person's group meeting slides that I poached from the internet to try to discover this.
Right. So this is linear, like y equals mx plus b, but then you can also have y equals like a x to the b or something like that, and b is exponential. So when you do your fit, you're getting 0.11, and here you're getting 0.7. So that's how I'm interpreting this. What you're telling us is that you're getting 0.11 for here, linear fit, and you're getting 0.7 for exponential. This one, we already have equations that relate current, or peak current more specifically, for random substance, relating it to the scan rate, right? So x in this case is the scan rate. So that's kind of, I guess, this is what I'm trying to interpret. And then this in particular, exponential, is the one that is mostly used, but you're using it to do a CDL calculation, which I don't know if I'm not 100% sure if that's what you're, because if you're doing CDL calculation, you only want to look at current versus scan rate in a non-Faradaic region, only when where it's like a rectangle, and then you want to do a scan rate study, and then you do a pure linear. Current is equal to the double layer times the scan rate, and that's a linear relationship. And maybe if you did that, if you got linear, you got 0.11, maybe that's just have to figure out the units, right? 1 amp is equal, I think 1 amp is equal to 1 farad times, I think it's volts per second. So keeping those units in mind, you can then figure out what the CDL is for your calculation. So hopefully that's helpful. He does have a follow-up question, which is also, can you tell the small semicircle obtained using Nova software is either RCT or RS, as when we use linear fit model, or either C1 plus R2 over C2, from that software, we tend to get another big semicircle too. And then we have two semicircles, but in many papers, the smaller semicircle is usually considered RCT. I think we need to know more about what your system is.
Yeah, I'm not sure I understand. Plus C1 plus R2 C2. I assume you mean R1 plus R2 C2.
Yeah.
You're not talking about a capacitor by itself. That's a bit bizarre. I assume you mean R1. If you have a semicircle, it's usually not RS.
Yeah.
If you have a semicircle, it usually refers to RCT. So a charge transfer resistance is usually coupled with the double layer capacitance, because those two processes are occurring in parallel around the same frequency range. RS is usually occurring at the higher frequencies, and it's not usually represented with a semicircle. It's the leftmost intercept on the Nyquist plot would be the resistance. Smaller semicircle. So yeah, again, I mean, I guess I don't really think about your system precisely here, but if you have two semicircles, you might have two processes occurring, or at least two interfaces. And so one of the reasons sometimes you get a small semicircle and a bigger semicircle is that the small semicircle is like the interface between substrate and film. And the bigger semicircle is your redox reaction that you're studying. Okay. One way to verify that is to change the applied potential. So for example, if you are studying some redox reaction, let me draw this out a little bit. I know we're almost at time, but if you have a like a substrate and a film, so you have an electrode of some kind, and you have some film on it or whatever, right? And then you have your electrolyte out here, and you're doing some redox, ORNE whatever. That's supposed to be an electron. Some redox process is occurring. When you do your nyquist plot, for example, at E applied is equal to E1, some applied potential, you might get like a small semicircle and then like a big semicircle. And then you change the applied potential, E is equal to E2, and you drive the reaction better. Sometimes what you'll see is that you'll get the same first semicircle, but you get a smaller second one. And so what this means is that this second semicircle is the charge transfer resistance. And this first semicircle here, this is the resistance at your substrate and your film. It's like the substrate film. The RS is the same in both of these. It's the leftmost intercept. But this here would be like our substrate film. I don't know. We can call it whatever you want. But because it doesn't change with potential, because it's a physical thing. It's not a redox reaction. That in this case, the redox reaction, the charge transfer resistance will decrease as the overpotential goes up. So something like that. But again, some of this I can't answer because we don't know exactly what your system is precisely. I'm just thinking as a possibility for what you're saying, one of the ways that kind of manifests itself. So,
well, we are out of time. I'm sorry. This is a lot of questions. We won't be in next week, but the following week we will be. Will you be here? December 8th, I think.
I'm gone that week, but I am here the
5th.
The 5th. I will be here the 5th.
December 5th.
I think I will be here the 5th.
Okay.
The following week.
Yeah, the following week, the week of the 8th. That's when you're out. Okay.
I am out, but I will be here the 5th. So we have a week off. We're back, and then another week off.
Yeah.
And then we're back.
And then we're back.
And then a week off because it's after Christmas.
Yeah,
probably
something like that.
Yeah.
All right.
So it will be a bit scattered as we get through the holiday season.
Yes.
We will get as many of these as we can because I know that some people are trying to get questions in on the, on the end of a semester here or whatever the case may be. We very much appreciate everybody. We got to the questions as fast as we can. Sorry if we haven't got to your question here being at the very end. Try to come a little sooner. And we're very sorry to have missed some people here.
Yeah.
We only have so much time for these live streams, unfortunately.
Yes.
Yeah. But we very much appreciate everybody, as always. And so if you're in the US, I guess we'll wish you a very happy Thanksgiving holiday. And if you're not in the US, I hope you have a miserable Thanksgiving holiday. Or you don't have a holiday at all, so just have a great week.
Have a great week, yeah.
I guess.
That's
some
true.
very nice thing to say.
Yeah.
So anyway,
all right.
Thank you, everybody.
Yep. And stay tuned to our YouTube channel and LinkedIn. We'll put upcoming live streams so you'll get the dates on our social media accounts. So you have to follow Pine Research to know more. And
if you have a question, we check those like every day actually. So if you have a question that you want to have asked, you can put it into the chat of a future live stream.
Yeah. We'll make sure they answer
2 weeks in advance or something, and we'll add it. We'll keep it and we'll add it, and we'll answer that first. We'll try to answer that first when the live stream starts because it was chronologically first.
Yeah,
technically, right?
Technically.
So we just try to answer them in a first come first serve basis as best we can. So, that's a good point. So check our YouTube channel for more, and we'll see everybody next time.
All right, have a good one.
Bye bye.